In this video, I'd like to continue the discussion on new integration methods, especially those that involve trigonometric substitutions. Now, in the last video, we talked a little bit about trigonometric identities and how they can be used to rewrite an integral and make it easier to work with. This new technique is what's called trigonometric substitutions. And what's particularly interesting here is that if an integral contains expressions that look something like this, where a is some number and x is our variable within the expression, then chances are we can use a corresponding trigonometric substitution, kind of like a u substitution, to rewrite our variable x in terms of a variable theta. And once we've rewritten in terms of a variable theta, then there's another trigonometric identity that becomes especially helpful in rewriting the expression. Now, this seems kind of tedious at first, especially as you're just learning the process and trying to recall your old trigonometric identities, but I assure you we're just going to be using this for practice and just to kind of illustrate a technique. We won't dwell upon this too much in this class, especially knowing that our table of integrals might be particularly helpful from time to time as well. But it's a neat process. It gives us a chance to review our trig identities, and it also shows us some of the algebraic techniques combined with geometry, if you will, that lead us to these nice shortcuts that our table of integrals does present. So here we go. Oh, and by the way, here's a YouTube video of another instructor online if you wanted to type that into your search box or your browser, if you will. This expression is case sensitive, but this person does a pretty nice job of explaining the trig substitutions as well. Okay, so in this particular case, it looks like I've got a value, a squared minus x squared, where a is equal to 3. So since I have a value that appears to be in that pattern, then I'm going to use this substitution. I'm going to state that x is going to be replaced with a times sine of theta. And much like our u substitutions, I'm just going to write this down off to the side. A is equal to, in this case, 3 sine theta. And while I'm at it, I'm going to compute the dx, just like we would have done if we had u and du. So the derivative of 3 sine theta is going to be 3 cosine theta d theta. Okay, so now anywhere that I see the letter x, I'm going to make the substitution with 3 sine theta. And so again, this may appear a bit messy at first, especially with these first few substitutions, but it tends to work out fairly nicely in the long run. So I'm going to write this square root. I'm going to write this as 3 squared, just to be consistent with the phrasing in the problem here, minus, now I need to write 3 sine theta squared. 3 sine theta has replaced x, and all of that's going to be divided by 3 sine theta squared. And then we can't forget that the dx is now being replaced with 3 cosine theta d theta. Okay, so that was a rather large substitution, and this expression is looking kind of nasty right now. But the benefit in doing this is observing this format here. We have a squared minus a times sine theta squared, or we could see this as, let's go ahead and rewrite it. We could do this with our eraser here. Instead of having the group 3 sine theta squared, we can actually call this 3 squared times sine squared. That way we don't have the parenthesis grouping. But now, again, what's helpful about this substitution and what just occurred is that this expression here is in the exact same format of this identity over here. Now, this is not an identity that we memorized in our trigonometric class, but it is one that shows up fairly frequently when using the trig substitution methods in calculus. So we have a squared minus a squared times sine squared, and we can actually substitute that with a squared cosine squared. And when we make that substitution inside of this square root expression, then we should start to see some really nice things occur. So we have 3 squared cosine squared theta. The square root of that is over, and I'll go ahead and write this one as 3 squared sine squared, and we're multiplying that still by 3 cosine theta. And actually, you know what I'm going to do is I'm going to multiply this in the numerator instead of on the side of the fraction, and you'll see why in just a moment. Okay. All right. So what happens when we take the square root of 3 squared times cosine squared? Well, that just leaves us with 3 cosine theta. Then if the result of this expression is 3 cosine theta, and we multiply again by 3 cosine theta, which was brought in by our differential, we're right back to where we started. We've got 3 squared cosine squared theta divided by 3 squared sine squared theta. And we want the integral of that with respect to theta. Okay, well, the 3 squareds can cancel, and now we just need to find the antiderivative of cosine squared over sine squared. Well, cosine squared over sine squared is tangent squared, so now we've simplified this antiderivative into the antiderivative of tangent squared theta, d theta. Sorry, that's cosine over sine, so that would be cotangent squared theta. And from our common trig identities, let's recall that cotangent squared would be equal to cosecant squared minus 1. So we can make that substitution. Let's jump back to the problem now. So this would be the integral of cosecant squared theta minus 1 d theta. And from one of the original derivative sets that we memorized, the antiderivative of cosecant squared is negative cotangent of theta. The antiderivative of negative 1 would be negative theta, and of course we can't forget about our plus c. And life would be great if we could report this as our final answer. This looks pretty nice. We went through some troubles to get there, but it does look good. However, the original problem was written with a variable of x, and our solution now has a variable of theta. So I don't want to leave this as it is. I would like to report our final answer in terms of x. Now here's where our trig substitution can get a little bit more complicated, but with a little bit of knowledge, again, with our basic trigonometry, we should be able to figure the rest of this out. I'm going to come back to this notion that we had started the substitution set with, and note that if x, let's separate these just a little bit, if x is equal to 3 sine theta, then x divided by 3 is equal to sine theta, and of everything that we learned in trig class, sine of a angle measure theta is equal to the ratio opposite side length divided by 3. So this particular expression is trying to illustrate a triangle that might look something like this. Let's draw a little bit more carefully. If I have an angle theta in question, the opposite side length has to be x, and the hypotenuse length has to be 3. And using a bit of right triangle trigonometry, 3 squared must be equal to this unknown value. You'll see why we need that in just a second. So this unknown value squared plus x squared. So the unknown value by itself would be the square root of 3 squared minus x squared. And you'll see why that's important in just a moment. Now, while we're here, we can make one last algebraic step on this equation too. If x divided by 3 is equal to sine of theta, then theta by itself would be sine inverse of x divided by 3. And I would argue that knowing this and this, we should be able to rewrite this. Here again, theta is equal to sine inverse of x divided by 3. And now negative cotangent. Well, this is kind of interesting. I don't need to solve for theta. I mean, that would be kind of tricky to apply cotangent of sine inverse of x divided by 3. Let's just recall that we're dealing with the right triangle here, where theta is located but not identified, and all three side lengths are located as well. So cotangent of some angle measure should be equal to the adjacent side length divided by the opposite side length. That's the definition of our cotangent trig function. So then we have a negative sign in front of the adjacent side length divided by opposite. Well, our adjacent side length we determined was the square root of 3 squared minus x squared, and we can divide that by the opposite side length of x. And now we've rewritten the final answer, not in terms of theta anymore, but now we've obtained it in terms of x. And if you'd like to check this answer with our table of integrals, if I'm not mistaken, you can find this at integral number 65 in that list. It's under the heading for integrals involving a squared minus x squared. So under that group, try number 65. This solution should match that layout pretty well. Let's try one more example in this video. Now in this case, I notice that there's an x squared plus 2 squared, or x squared plus a squared here. So to me, that looks like this format. The order's slightly different, but that's the format that we're dealing with. So if I'm dealing with an a squared plus x squared, then the substitution that I want to use is a tangent theta. So I'll switch to a different color here to make this one stand out. Okay, so x is going to be the result of, in this case, 2 tangent theta. So dx is equal to 2 secant squared theta d theta. And we can start these substitutions and see where this algebra leads us. So we're going to write the integral of 1 over, now x squared is going to be reported as 2 tangent theta quantity squared times the square root of, again, 2 tangent theta squared plus 2 squared dx. Now we're not going to report this in terms of dx, we'll write it in terms of d theta. And dx, well, let's just go ahead and report it up here. It's going to be 2 secant squared theta d theta. Okay, so the substitution's been made. This expression is an identity that's helpful to us, and that's reported in this nice summary box. By the way, this box came from Math Excel, so you can thank them for putting it together for us. When we see 2 squared plus 2 squared times tangent squared, we can replace that with 2 squared times secant squared. So this element inside the square root symbol is going to be replaced. So we've got some copying to do here. 2 secant squared theta divided by, we'll call this 2 squared tangent squared theta times the square root of 2 squared secant squared theta d theta. And those that are quick will recognize, just like we saw in the last example, there's a square root of the product of two terms that are being squared themselves. So if you'd like to jump this step and create this shortcut, that would be okay. The square root of 2 squared secant squared is just 2 secant theta. And since we've made that change, we might also note that 2 secant squared theta is really just 2 times secant theta times secant theta. It's nice working with a writing utensil that has an eraser, isn't it? But I'm not going to erase anymore. I'm going to copy the next line. But again, the hope here is to find some items that'll start to cancel. And as it turns out, this 2 secant theta can cancel with this 2 secant theta. And we're left with kind of an interesting result. We've got a 1 as a coefficient in the numerator and a 4 in the denominator. So I'm going to move this constant out front, 1/4, and we have secant theta divided by tangent squared theta d theta. Now, as a side note, secant theta divided by tangent squared theta is really the same as secant theta times cotangent squared theta. And secant theta is 1 divided by cosine theta, and cotangent theta is cosine divided by sine. So cosine or cotangent squared is cosine squared divided by sine squared. And this is then going to reduce to this next step that I wanted to show. We'll have a cosine in the numerator because 1 would cancel here with the denominator. We have cosine theta divided by sine squared theta d theta. And again, the work here has gotten kind of messy. We've been able to rewrite in a couple different ways, but this particular expression is fairly nice, believe it or not. Let's just jump up here and continue with it. A quarter of cosine theta divided by sine squared theta d theta. And what I'm going to note here is that there's an inner function, sine theta, whose derivative exists elsewhere in the problem. That's cosine theta d theta. And so now wherever I see cosine theta d theta, and anywhere that I see sine theta, I can make appropriate substitutions. And we're left with a rather, dare I say it, nice expression, 1/4 of 1 over u squared du. I'm going to call this u to the negative second power du. And if we finish this integration, we get 1/4 times u to the negative first power divided by negative 1 plus c. And this looks an awful lot like negative 1 over 4u plus c. But here again, we've got a problem. We can't leave our answer in terms of u, so we better back substitute. And we might call this, let me give myself some room here, negative 1 over 4 sine theta plus c, because again, this u is the same as sine theta. But our original problem was not in terms of theta either. It was not u, it was not theta. We've got to get it back to x. So let's use a triangle then and make that correction. We saw this trick before, that if x is equal to 2 tangent of theta, then x divided by 2 is equal to tangent of theta. And that would represent a right triangle that has these characteristics. We'll place theta down here again. The opposite side length is x. The adjacent side length is 2, because we want opposite over adjacent. And therefore, the hypotenuse length is the square root of x squared plus 2 squared. Well, if that's the relationship of tangent theta, then sine theta certainly would be the opposite side length x divided by the hypotenuse, which is the square root of x squared plus 2 squared. So here we go, final answer perhaps. We have negative 1 over 4 times sine theta, and sine theta was just established as x divided by square root x squared plus 2 squared, and all of that plus c. Now, I'm okay with this as a final answer. However, since we are using Math Excel, they may request that this is simplified a bit further. And so the only thing that I think we might encounter is this notion of the fraction inside of a fraction. And to address that, I might consider the following. If we imagine this 4 distributing into this fraction down below, we'd end up with 4x right here. And now we've got the number negative 1 divided by this fraction. Well, if we recall, to divide a fraction, we could multiply by the reciprocal. So we could take negative 1 and multiply by the square root of x squared plus 2 squared over 4x. And with this negative 1 multiplier, we don't really need to show the 1 perhaps. and so we can just write this as a negative sign in front of this fraction plus c, and that might be a nicer way to report our final answer. Now here again, this particular antiderivative question has a format that does fall into our trig table, or sorry, our table of integrals, and if I'm not mistaken, this one's number 77. Sorry, number 79. So if you want to consult the table of trig integrals number 79, you can see if our trig substitution led us to the same result. Now clearly, completing these trig substitutions over and over again can be very, very tedious. It is time consuming, but it's a neat technique to show the derivation, if you will, of those trigonometric rules, those integral rules that we had just referenced inside of our table. So I think it's a neat thing to see, and worth learning technique a time or two here in class. In the next video, we'll cover the last component of this unit, and that's where we integrate using partial fractions. Thanks for watching.